All right, welcome to the class. From today on, we're going to have a look at chapter 9, waves and light. So there are 5 sections in this chapter. Today, we're going to have a look at the first 2 sections. So today is the first lesson of chapter 9. We're going to have a look at properties of waves and light, and then refraction and total internal reflection. So if you have ever gone surfing at a water park or in a lake or on ocean, or watched a news report about tsunami, you know that water waves can transmit a large amount of energy, which is shown here in figure 1, right? Other examples of waves are mechanical waves, such as a wave on a vibrating string or the surface of a ring bell. Sound waves such as AM and FM waves and seismic waves produced by earthquakes. All waves share the same basic properties. Okay, so let's have a look at the common properties of waves. A wave is a moving disturbance that transports energy from one place to another, but doesn't necessarily transport matter. The simplest wave is periodic wave. A periodic wave is a wave that repeats itself at regular intervals. So here, as shown in figure 2, it illustrates one way to generate a mechanical wave. In figure 2a, the person's hand exerts a vertical force on the spring, creating a wave pulse. Since the force and resulting pulse act along the length of the spring, the force does work on the spring. This means that the wave pulse carries energy along the string from the hand to the wall. In figure 2b, as the hand continues to move, the wave becomes periodic. Also notice that the points on the strings or metal does not move horizontally, right? So suppose that the person is shaking the string such that the string is moving in a periodic fashion in the vertical direction. Figure 3 shows a snapshot of the waves as it begins to move to the right. So the front edge of a wave is called the wave front. Here, careful with the concept of wave front. We're going to use this a lot. The crest of a wave is the upper half of the wave, and the trough of the wave is the lower half of the wave, as shown here in figure 3. One complete crest and one complete trough represent one cycle of the wave. The amplitude, which is often denoted by uppercase letter A, is the maximum and minimum value of the wave, which is shown here in figure 4. The wavelength, denoted by lambda, of the wave is the distance from one positive amplitude to the next positive amplitude, or one negative amplitude to the next negative amplitude. 2 points on the wave that are at the same place in a wave cycle, for example, 2 successful crests, are said to have the same phase. Generally, the phase is offside of the wave from the reference point. The period, denoted by uppercase letter T of a wave, is the time required for one wave cycle to pass a particular point. And the frequency, denoted by lowercase letter f, is the number of wave cycles that pass a particular point per unit of time. The SI unit of frequency is hertz, or abbreviated as HV. 1 hertz is equal to 1 cycle per second. So how can we use these properties to measure the speed of a wave. Here in figure 4, it shows that the wave moves a distance of delta x equals lambda during a period of motion, or delta t equals uppercase T. The following equation determines the speed of the wave, as shown here. First of all, we have v equals delta x over delta t, right? Then we know that's actually lambda over delta t. Frequency f and period t are related according to the following relationship. F equals the reciprocal of t, or t equals the reciprocal of f. Substituting the equation for period into the equation for v, you can see that v equals lambda over the reciprocal of f, or we have this formula here. V equals lambda f, or f lambda. So this is called the universal wave equation, and it shows that the speed of a periodic wave is related to its frequency and wavelength. A unit analysis of this equation shows that the frequency in hertz corresponds to speed in meters per second. Any questions? Okay, so basically the speed of a wave equals the frequency of the wave times the wavelength. Okay, next, let's have a look at a concept called reflection. In many instances, light travels in straight lines. This model, which treats the propagation of light waves as though they move in straight lines, is called ray approximation. So here in figure 5a, it shows a reflection of a light modeled by rays. Reflection is a change in direction after meeting an obstacle. For example, a mirror, where the original ray and the reflected ray on the same side of the obstacle or mirror. Figure 5c shows the angle of incidence, denoted by theta I, and the angle of reflection, denoted by theta r, of one of the rays. So consider the reflection of light from a flat mirror. The normal line is a reference line drawn at the right angle to the surface of the mirror. The angle of incidence is the angle between the incoming or incident ray and normal, which is here. Right? This is the angle of incidence. On the other hand, the angle of reflection is the angle between the outgoing or reflected ray and the normal, which is here. This is called the angle of reflection. Light then behaves according to the law of reflection, which states that for reflection from a flat surface, the angle of incidence is always equal to the angle of reflection. The reflections from a flat surface, such as the reflecting surface shown in figure 5, are called specular reflections. However, if the reflecting surface is rough, as shown here in figure 6, then the reflected rays are directed in many different directions as light strikes the different parts of the surface. This is called a diffused reflection. See the difference? Specular reflection and diffuse reflection. So basically, the specular reflection is the reflection of light from a surface where all the reflected rays are in the same direction, whereas diffuse reflection means the reflection of light from a surface where all the reflected rays are directed in many different directions. Any questions? Okay, so these are the very basic concepts in this chapter. So next, let's have a look at the second section of this chapter, which is about refraction and total internal reflection. So when a light wave strikes a transparent material, such as glass or water, some of the light is reflected from the surface. We have discussed this in the previous section, right? The rest of the light passes through or transmits the material. Figure 1 here shows a ray that enters a glass block that has two parallel sides. The part of the original ray that travels into the glass is called the refracted ray. And the part of the original ray that is reflected is called the reflected ray. Refracted and reflected rays of light account for many things that we encounter in our everyday lives. For example, the water in the pool can look shallower than it really is. A stick can look as if it bends at the point where it enters the water. On a hot day, the road ahead can appear to have a puddle of water, which turns out to be a mirage. These effects are all caused by the refraction and reflection of light. Okay, so now let's have a look at the concept of refraction in detail. The direction of the refracted ray is different from the direction of the incident ray, an effect called refraction. As with reflection, you can measure the direction of the refracted ray using the angle that it makes with the normal. Here in figure 1, this angle is labeled with theta 2. The size of this angle depends on the incident angle, which is shown as theta I in figure 1 here, as well as the optical densities of the two media. The optical density of a medium is a measure of its tendency to absorb the energy of an electromagnetic wave, which is different from the material's mass density. The more optically dense a material is, the slower a wave will move through it. Then, when light travels from a less optimally dense medium, such as air, to a more optically dense medium, such as glass, light is refracted towards the normal, as shown here in figure 1. If we extend the refracted ray in figure 1 to show the light leaving the glass and entering the air again, you would see that the light is refracted away from the normal and emerges parallel to the incident ray. This is shown in here, figure 2. It's an example of the principle of reversibility, which states that the path a light ray follows remains the same if its direction of travel is reversed. So consider the speed of light in various media. The speed of light in vacuum is approximately 3.0 times 10 to the power of 8 meters per second, right? In most cases, this value is a good approximation of the speed of light in air. However, when the light enters a different medium, it interacts with items and its average speed through the medium is changed. The ratio of the speed of light in a vacuum to the speed of light in another medium, or C over V, is called the index of refraction, which is denoted by letter N. Okay, so index of refraction N is defined as C over V. V is the speed of light in another medium, and C is the speed of light in a vacuum, which is approximately 3 times 10 to the power of 8 meters per second. This is a good approximation in most of the cases. So here, table 1 on this page shows the speed of light and indices of refraction in different media. You can see the speed of light in the air is very close to the speed of light in vacuum, right? So in most of the cases, we use the speed of light in vacuum as approximation as the speed of light in the air, which is approximately 3 times 10 to the power of 8 meters per second. So notice that in table 1, as index of refraction increases, the speed of light in various medium decreases. Okay, can you see the tendency here? As the index of refraction increases, the speed of light in that medium decreases. Okay, so figure 3 here shows how the change in the speed of light from a vacuum to glass affects the orientation of the wavefronts and direction of the ray inside the glass, causing refraction. Each incident ray is at a right angle to its respective wavefront. The incident rays arrive at angle of θ1, and the refracted rays are at angle of θ2. It also shows the wavefronts at equally spaced moments in time. The speed of light in the vacuum is c, right? So the wave travels a distance of ct through the vacuum is in time t. In the glass, the speed of light is reduced to v. So the wave travels a distance of vt in the same time t. Since the speed of light in a vacuum c is greater than the speed of light in the glass v, the distance traveled in time t in the glass is less than distance traveled in vacuum ct. This effect causes a wavefront to bend at the point where they enter the glass, which means that the light rays bend towards the normal as they enter the glass. The result is that θ2 is less than θ1. The angle θ2 between the refracted light ray and the normal is called angle of refraction, as we have discussed earlier, and is often written as θr. So next, let's have a look at figure 4 here. Figure 4 shows a more detailed view of the relationship between the angle θ1 and θ2 as the wavefronts enter the glass. Okay, so have a look at this figure in detail. The orange triangle on the glass edge in this figure has size of length CT and L, right? So CT is here, L is here, with the angle adjacent to L being θ1. The following trigonometric relationship is true for this triangle. We have θ1, or sine θ1 equals CT over L, right? This is by definition in a right triangle. The corresponding yellow triangle has size of length VT and L, with the angle adjacent to L being θ2. So according to trigonometry, we can easily obtain this relationship. Sine θ2 equals VT over L. So we can rearrange these equations to solve for L. First of all, L is CT over sine θ1. On the other hand, L is also VT over sine θ2. Therefore, we have this equality relationship. CT over sine θ1 equals VT over sine θ2. Since t cannot equal 0, we can divide each side of the equation by t, which gives us c over sine θ1 equals v over sine θ2. Or you can also write it like this: sine θ1 equals c sine θ2 divided by v. Recall that the ratio c over v here, c over v, is called the index of refraction, right? And is given by the symbol n, which is here, n equals c over v. Therefore, we have this relationship here. Sine θ1 equals n2 times sine θ2, where n2 is index of refraction of the glass. The preceding derivation describes the refraction of light from a vacuum to glass. If you consider the common situation where light passes between two substances, such as air and glass or air and water, then the following relationship called Snell's law is true. We have the Snell's law here, which gives us the relationship n1 sine theta 1 equals n2 sine theta 2, where n1 and theta 1 are respectively the index of refraction in the incident medium and the angle of incidence. On the other hand, n2 and theta 2 are respectively the index of refraction for the medium being studied and the angle of refraction. Using the relationship between speed, frequency, and wavelengths, as well as the fact that the frequency of light does not change when passing from one substance to another, the following equation can also be derived. First of all, n equals c over v, right? On the other hand, we know c over v can be represented by f lambda 1 over f lambda 2. Since the frequency does not change, we can cancel same frequency here. So n equals lambda 1 over lambda 2, where lambda 1 is the wavelength of light in medium 1, sorry, in substance 1, and lambda 2 is a wavelength in substance 2, where the first medium is not a vacuum. When the first medium is not a vacuum and has index of refraction n1, this equation then becomes here. n2 over n1 equals lambda 1 over lambda 2, or you can also express this using the product instead of a ratio. This one is much easier to memorize, right? n1 lambda 1 equals n2 lambda 2, which is similar to this equation here. So we have derived two important relationships. One of them is called Snell's law, which is n1 sine theta 1 equals n2 sine theta 2. Another one is here, n1 lambda 1 equals n2 lambda 2. Again, lambda 1 is the wavelength in substance 1, and lambda 2 is the wavelength in substance 2. Okay, I'll give you some time to have a look at this relationship here. Any questions, just let me know, okay? All right, if you don't have any questions, let's have a look at figure 5 here. In figure 5, incident light hits a block at angle θ1 on side 1. It's then refracted at angle θ2, which can be calculated using Snell's law. If we have enough information, such as indices of refraction of the media, when the incident light hits the boundary of the opposite side at an angle θ2, the light is refracted at an angle equal to θ1 because the surfaces are parallel. Okay, so this is just an example. So next, let's have a look at a problem in which we'll use Snell's law to solve it. Okay, let's consider this problem here. Can you calculate the angle of refraction for light moving from a vacuum into a plate of glass with index of refraction 1.47? Also, we know the angle of incidence is 40.0 degrees. Next, second question. The light continues through the glass and emerges back into a vacuum. Calculate the angle of refraction when the light exits the glass. Question C, suppose the light exits into water instead of vacuum. Can you calculate the angle of refraction for the light moving from glass into water? The index of refraction water is given to be 1.33. Okay, I'll give you 5 minutes to consider this problem, and then we'll have a look at the solution together. Okay, let's have a look at the solution here. So in the first question, we can use a Snell's law to find the angle of refraction, right? So here we know theta1. We also know n1 and n2. So sine theta2 is the angle of refraction. So sine theta2 equals n1 sine theta1 over n2, right? Put all the values in, we have sine theta2 is approximately 25.9 degrees. So the angle of refraction for light moving from the vacuum into glass is approximately 26 degrees. In question B, we can use the other form of the Snell's law, which is n3 sine theta 3 equals n2 sine theta 2, right? So that gives us sine theta 3 is n2 sine theta 2 over n3, which is approximately 0.64. Therefore, theta 3 is approximately 40 degrees. So the angle of refraction for light moving from the glass back into the vacuum is 40 degrees. This is the same as the angle of incidence of the ray entering the glass. Okay, in question C, we know N3 is 1.33, theta 2 equals 25.9 degrees, and N2 is 1.47. Again, we can use a Snell's law. We have sine theta 3 equals N2 sine theta 2 over N3. So that'll give us sine theta 3 is approximately 29 degrees. So the angle of refraction for light moving from glass into water is 29 degrees approximately. Any questions? No? Okay, then let's have a look at another problem. Light travels at 3.0 times 10 to the power of 8 meters per second. Laser light with a wavelength of 520 nanometers enters a sheet of plastic. The index of refraction for the plastic is 1.49. So these are the given information. Based on this information, there are 3 questions you need to answer. First, can you calculate the speed of laser light in the plastic? Then calculate the wavelength of laser light in the plastic. Last, calculate the frequency of the laser light in the plastic. Okay, again, I'll give you 5 minutes to consider this problem by yourself. Then we'll have a look at the solution together. All right, next, let's have a look at the solution together. In question A, note that we can use the formula V equals C over N to get the speed of light in this substance. So put all the values in. C is the speed of light in vacuum, which is 3 times 10 to the power of 8 meters per second. N is the index of refraction of the light in these substances. So the speed of laser light in the plastic is 2.0 times 10 to the power of 8 meters per second. In question B, according to the derived formula from Snell's law, we know lambda 1 and 1 equals lambda 2 and 2, right? So lambda 1 is the wavelength of this laser light in vacuum. N1 is the index of refraction of the light in vacuum, which is 1, right? And N2 is the index of refraction in the plastic. And lambda 2 is the wavelength of this light in this plastic. So we have lambda 2 equals lambda 1 over N2. So in this case, we can just use N because N1 is just 1, right? So lambda 2 equals lambda 1 over N, which is 5.2 times 10 to the power of -7 meters over 1.49. So that gives us lambda 2 equals 3.49 times 10 to the power of -7 meters. So the wavelength of laser light in this plastic is approximately 3.5 times 10 to the power of -7 meters. Okay, last question. We know the speed of light equals the wavelength of the light times the frequency of the light. So we can use this formula to find the frequency directly. Frequency is just the speed of this light over the wavelength. Put all the values in, we have the frequency of this light is 5.77 times 10 to the power of 14 hertz. Any questions? Okay, if you don't have any questions, let's take a 10 minutes break. And after that, we'll have a look at the second part of this lesson. Okay, welcome back. So next, let's have a look at the concept of dispersion and prisms. Visible light contains waves with a spectrum of different wavelengths. In a vacuum, all these waves travel at the same speed, which is 3 times 10 to the power of 8 meters per second. When visible light travels from one media to another, the speeds of various waves change. The speed of the wave depends on its frequency and wavelength. When the waves enter new medium, its frequency does not change, but its wavelength does. This means that the speed of the refracted light depends on its wavelength. This dependency of speed of light on wavelength causes light waves to separate in a phenomenon called dispersion. Here, figure 6 shows the variations of the speed of visible light with wavelengths for 3 materials. So here's the index of refraction for a material depends on the wavelength of light. The index of refraction for a red light at one end of the visible spectrum, and the index of refraction for blue light at the opposite end of the spectrum are slightly different for the same material. For example, figure 6 here shows that in quotes, the index of refraction for red light is approximately 1.46, and the index of refraction for blue light is approximately 1.47. The difference between these values is 0.01, which is much smaller than the difference between the average indices of refraction for quartz and water, in which the difference is 1.46 minus 1.33, which is 0.13. However, the difference is large enough to lead to a difference in the angle of refraction for different colors in quartz. This is true in other materials as well. So here in figure 7, it shows how the effect is used in a prism to disperse or separate an incident beam of white light into its component colors. Prisms are often composed of glass and are triangular in shape, as shown in figure 7b. In figure 7a, the beam of light that is incident on the prism is taken, for simplicity, to be composed of two colors, red and blue, represented as two rays. Each ray is refracted once when it enters the left-hand face of the prism, and again when it leaves the prism at the right-hand face. Note that the light does not curve within the material, but only changes direction at the boundaries. The incident blue light has a slightly larger index of refraction than red light, so its angle of refraction is less than the angle of refraction of the incident red light. Inside the glass, the blue and red light components travel along slightly different paths. This path difference is increased by the second refraction when the light exits the prism. The outgoing light appears slightly bluish at one side and slightly reddish at the other side of the beam. Another effect of the triangular shape of the prism is that the light ray leaving the prism is not parallel to the light ray that enters the prism. The angle between the incident ray and the final outgoing ray is called the angle of deviation. Okay, next let's consider a sample problem in which we can use Snell's law to solve dispersion problems involving prisms. Okay, so let's consider this question here. Figure 8 here shows a ray of light incident on a glass triangular prism. It's refracted as it passes through the first phase and is then refracted again through the second phase. There are 3 questions. Okay, I'm gonna show you the 3 questions here. Okay, consider these 3 questions. A, calculate the angles of refraction for blue light and for right light traveling from air into the left boundary of the prism. The angle of incidence at the left boundary of the prism is 40 degrees. The index of refraction for blue light in the prism is 1.47, and index of refraction for red light is 1.46. The index of refraction for air is 1.0003. Question B, calculate angle of incidence for blue and red light at the right boundary of the prism. Then calculate the angle of refraction for blue and red light as the ray exits the prism. Okay, I'll give you 10 minutes to consider this question, and after that, we'll have a look at the solution together. All right, let's have a look at the solution together. Okay, consider question A first. Okay, we are given the following information. We know the index of refraction N2 blue is 1.47, and N2 red is 1.46. And index of refraction in the air is 1.0003. Theta1 is 40 degrees, right? So according to Snell's law, we have the following relationship. Sine theta2 over sine theta1 is N air over N prism. So solve for blue light gives us sine theta2 blue equals N1 sine theta1 over N2 blue. So that gives us about 25.94 degrees. So using the same method, we can solve theta2 red is 26.13 degrees. So the angle of refraction at the left boundary of the prism of blue light is 25.9 degrees, and angle of refraction of red light is 26.1 degrees. Okay, next let's have a look at question B and C. So in question B, if theta2 is the angle of refraction at the left boundary and theta3 is the angle of incident of the right boundary, then from the geometry of the triangular prism, we have theta2 plus theta3 equals 60 degrees, right? Which is the angle in the top right of the triangle. Then theta3 equals 60 degrees minus theta2. So for blue light, we have 60 degrees minus 25.94 equals 34.06 degrees. And for red light, we have 60 minus 26.313 equals 33.87 degrees. So the angle of incidence at the right boundary of the prism of blue light is approximately 34.1 degrees, and the angle of incidence for red light is 33.9 degrees. So in question C, the method is similar to what we have used in question A. So for blue light, we have sine theta4 blue over sine theta3 blue equals N2 blue over N1. So that gives us theta4 blue equals 55.4 degrees. For red light, theta4 red is 54.4 degrees. So the angle of refraction for the blue light as its axis of prism is about 55.4 degrees. And this angle for red light as its axis of prism is 54.4 degrees. Okay. All right, next let's have a look at a concept called total internal reflection. So the angle of refraction depends on the angle of incidence. However, for some values of the angle of incidence, there is no reflected ray. Consider a light ray that travels in medium 1 and meets the boundary of medium 2, as shown here in figure 11. If the index of refraction N1 is greater than N2, the angle of refraction theta2 should be greater than theta1, right? This is according to the Snell's law. Light will refract away from the normal. As the incident angle theta1 increases, the refracted angle theta2 also increases. Where theta2 reaches 90 degrees, the refracted ray will travel parallel to the surface, which is shown here in figure 11b. The value of the angle of the incidence at which this occurs is called the critical angle, which is denoted by letter beta c. If the angle of incidence theta1 increases beyond the critical angle, there is no refracted ray, and the incident light ray is totally reflected at the boundary, which is shown here in figure 11c. This effect is called total internal reflection. This effect can occur when light encounters a boundary between an initial medium with a higher index of refraction and a second medium with a lower index of refraction. So here, figure 12, which is shown on the bottom left, this is an example of total internal reflection. Here, light from a laser enters the side of a tank of water and travels through it. At the air-water boundary, the angle of incidence exceeds the critical angle, so there is no refracted ray. The ray is reflected as though it had hit the surface at a mirror. The incident and reflected rays obey the law of reflection, where theta I equals theta R. By applying the Snell's law, we can determine the critical angle since theta 1 equals theta C and theta 2 equals 90 degrees, right? So from Snell's law, we have N1 sine theta 2. Here, N1 sine theta C equals N2 sine theta 90 degrees, which equals N2. Therefore, we know sine critical angle theta C equals N2 over N1. Therefore, we can find the critical angle theta C. Since the sine of an angle can never be greater than 1, there can be no critical angle unless N1 is greater than N2, right? This means that total internal reflection only occurs when light travels through a medium and encounters a boundary of another medium with a lower index of refraction. On the other, in other words, N1 must be greater than N2. Any questions? Okay, so total internal reflection can occur even when the medium appears to be otherwise transparent. If you look carefully at the glass of water, you can observe that at certain angles, you do not see the table on which the glass sits. Instead, you see a reflection of the inside of the glass. However, if you pick up the glass, you will immediately see your fingers. Total internal reflection has many practical applications. When combined with glass or prism, total internal reflection can change the direction of a light ray, as shown here in figure 13. Prisms that are isosceles right-angled triangles are often used to control direction of light. As figure 14a here shows, light enters from a side is turned 90 degrees and exits out the other side. Figure 14b shows how to use the two short sides of prism to make the light entering the base. Take two 90 degrees turns before exiting back out the base. Figure 14c shows an application in which two prisms are used together to alter the path of a ray of light, as in the periscope of a submarine. The retroreflectors left on the surface of the moon by astronauts during some of the Apollo missions are an interesting application of the reflection of light. These retroreflectors, as shown here in figure 15, contain hundreds of prisms and are oriented to reflect laser light back to Earth, much like the reflector on a bicycle. These retroreflectors have the property of always reflecting an incoming light ray back in the direction it came from. When scientists aim a laser at a retroreflector on the moon, the reflection enables them to measure the Earth's moon distance with a precision of about 15 centimeters. You can also make use of total internal reflection and dispersion to achieve a filter light effect using a semicircular piece of glass, as shown here in figure 16. If a ray of light travels towards the center of the semicircle at point P, it will strike the round edge along the normal and not refract. Imagine now rotating the piece of glass to make larger angles of incident. Because the index of refraction depends on wavelengths of light, the critical angle for the glass-air interface also depends on the wavelengths of light. In fact, the critical angle for blue light is less than the critical angle for red light. Therefore, as the angle increases, the light emerging along the flat edge of the glass becomes increasingly red in color as other wavelengths totally reflect. Okay, so now let's have a look at fiber optics, which is a technology that uses flexible strands of glass called optical fibers to conduct and transmit light. Recall that light undergoes partial reflection and refraction when it encounters an interface between materials with different indices of fraction. Although an optical fiber is cylindrical, its diameter is large compared to the wavelengths of light. Consequently, the reflection of light within the optical fiber is similar to reflection from a flat interface. Even if the fiber is curved, the light remains inside due to total internal reflection, which is shown here in figure 17. The optical fiber in figure 17 is a simplified illustration. All practical optical fibers consist of at least two different types of glass, which is shown here in figure 18. The central core is surrounded by an outer layer called cladding. The core and the cladding are both made of glass, but with different compositions and different indices of refraction. The index of refraction of the cladding is less than the core's index of refraction, enabling total internal reflection of light within the core. In an application, light from a laser enters the fiber at one end, such that the angle of incidence permits the light to always undergo total internal reflection at the boundary between the core and the cladding. Signals such as a telephone signal are carried from one end of the fiber to the other by pulses of laser lights within the core. These fibers can be very long, many kilometers, and a simple fiber can carry many more simultaneously signals than is possible with a conventional metal wire. Optical fibers can be quite flexible, and an optical transmission line can be constructed by bonding parallel fibers together. The range of the angles at which light can enter the fiber is called the acceptance cone, which is shown here in figure 19. If incoming light is at an angle within this cone, then it will be transmitted through the fiber by total internal reflection. If incoming light is at an angle outside this cone, then it can exit out of the fiber cone. The size of the acceptance cone can be adjusted. It would become larger if the critical angle for the cone were made smaller. Using a material with a smaller index of refraction for the cladding material makes the difference between the indices of refraction for the core and cladding materials greater. If a fiber optic cable bends too much at one point, an incident light ray can hit the side of an angle less than theta c. or the critical angle, the possibility of total internal reflection is lost, and the light can exit the cone fiber. If a light ray traveling inside the fiber meets the side wall of a fiber with angle of incidence θ1, there is a reflected ray with an angle of there is a there is a reflected ray with an angle of reflection equal to θ1. However, if the fiber is bent to the point that θ1 is less than the critical angle θc, then total internal reflection is lost. The refracted ray in the air travels at an angle θ2, and there is a loss of light within the fiber. The fiber optic cables can be made very small and flexible, so they have many uses for transporting signals and light through small and dangerous places. Doctors can study a patient's internal tissues using an instrument called an endoscope, which is shown here in figure 20, which uses fiber optics. With an endoscope, a doctor can check a patient's digestive system for internal blockages, damaged tissues, stomach ulcers, and other medical issues without performing major surgery. Fiber optic cables have transformed communications by allowing signals to travel quickly at the speed of light across long distances with relatively little loss of signal strength. Silica fibers, which are commonly used, have a loss rate approximately 5% to 10% of the signal intensity per kilometer. There are some cables with losses of less than 5%. However, over large distances, technicians have to boost the signal along the way to take care of the signal intensity losses. Many communications companies in Ontario, in Canada here, depend on fiber optic technology for internet and telephone services. Even transatlantic cables, which were once made of metal, now consist of fiber optic cables, including the CAN-TAT3, which run from Nova Scotia on the western end to Iceland, the Faroe Islands, England, Denmark, and Germany on the east end. Okay, so now let's consider a problem here. First, calculate a critical angle for light passing through water, which has index of refraction 1.33, into air, which has index of refraction 1.3330. Next, describe what an underwater swimmer sees if she looks towards the surface at angle of 40 from A and 6 degrees relative to the normal. Okay, I'll give you 5 minutes to consider this question here, and after that, we'll have a look at the solution together. All right, let's have a look at the solution together. Okay, question A, according to the formula to calculate the critical angle, we know sine theta c equals n2 over n1, right? Therefore, theta c is arc sine of n2 over n1. To put all the values in, we have theta c is approximately 48.8 degrees. So the critical angle for light passing through water into air is 48.8 degrees. So in question B, the path of a light ray is reversible. So a light ray that reaches the swimmer's eye must travel the same path as the light ray that leaves the swimmer's eye. The 40 degree angle is less than the critical angle, right? A light ray directed from the swimmer's eye to the surface at an angle less than the critical angle will pass through the surface. So the swimmer sees light from outside the water when she looks at an angle of 40. A light ray directed from her eye to the surface at a critical angle will travel along the surface. So the swimmer sees light traveling along the surface when she looks at theta c. Well, in the third case, the 60-degree angle is greater than the critical angle. A light ray directed from her eye to the surface at an angle greater than the critical angle will reflect from the surface back into the water. So she sees light from underwater when she looks at angle 60 degrees. You see the difference? Okay, so that's the major key points for today's lesson. I'll see you next time. Bye.